today, I'm very pleased to have Alana Fish here from the University of Alberta. Alana did her undergraduate and master's work at the University of Alberta in computer science, right, or computational science there. Did her PhD work in machine learning at CMU and is now back at the University of Alberta on the faculty there, jointly appointed in computational science and psychology. And as you'll see today, it hits a really interesting intersection of serious machine learning, especially the NLP, natural language processing sort of side of things, trying to understand learning, and neuroimaging. So excited to hear about her work today, trying to understand how language is represented and language is learned in the brain. So Alana, we're very glad you're here. Thanks for joining us.
Thank you so much. Very nice introduction. Okay, so that's the general idea. Today we're going to talk about language in the brain, in particular how it is that you might learn a new language and what that looks like once you've learned a new language. So language is easy once you've figured it out. So kids have to work really hard to learn language, but if I'm doing a good job today, as I talk, language will just fall away. You'll forget that I'm even talking to you. And when you're really in depth in conversation, it's like language isn't even part of what you're thinking about. You're thinking about the concepts and the thoughts, right? So that's native language, that's fluent language. And that's what a lot of the work has focused on. So today instead we're going to talk about what it means to learn a language. Now learning a language is of course much more difficult. It's effortful, it takes a lot of practice, and it's something you have to work at. Even once you've learned the language, speaking in the language that's not your native language can be hard. So today we're going to talk about the neural processes that are behind learning a new language and what that means in the brain. So a lot of the previous work has focused on native language understanding. So they put people in a scanner, they take pictures of their brain while they read words in their native language, and we try to figure out what their brain is doing. So this is a slight departure, and that was what all of my work up until this point was on. This is a slight departure in that we're going to ask them to learn a new mapping of symbol to word, and then we're going to ask if we can still pick up that word representation in their brain when they see the symbol. So the questions we're going to answer today are, can we detect learning? So can we tell that a person is actually learning the mapping that we're asking them to learn? And can we detect the content of the learning? So though I'm showing you a symbol instead of the word cow, can I tell that you're thinking of the word cow? So you've learned the mapping from symbol to cow. Can I see that new mapping in your brain? And then we're also interested in how that learned mapping, how the representation induced by the new learned mapping is different than the representation induced by the original word form. So how is reading the symbol that you've learned means cow different from reading the word cow? So this is in collaboration with a few of my collaborators at UVic. I was at UVic until just recently. I just moved in July. So this is my student Chris Foster. He's going to forever regret putting on this EEG cap and then taking his picture, because I use it in all of my talks. I'm sure he doesn't appreciate it. As well as Chad Williams and Olaf Krugolson. So Chad is actually the one who collected the data, and Olaf is his supervisor. So you may not have heard of the University of Victoria, so I thought I would just tell you. Here is Victoria. It's actually really close to Seattle, and it's actually south of the American mainland border. So it's one of the most southerly places in Canada. And in addition, it gets less rain than Vancouver. And it gets no snow. It doesn't freeze. It doesn't get below freezing. It's very rare. So that's where I used to live. I lived there for 3 years, and now I live in Edmonton. Edmonton is not south of the mainland border. It does get snow. You may wonder why I moved. If you have questions about that, we can talk during the break. But Victoria is beautiful, and my collaborators there are fantastic. Okay, so this is generally the flow of what we'll talk about today. So we're going to talk about how we find language in the brain. So this is the typical studies I've done up until this point, looking at native language and native language representations in the brain. Then we'll talk about the paradigm we use to get people to learn this new mapping between symbols and their native language. And then we'll go through the results, and then we'll wrap up at the end. So at the beginning, we need to talk about how computers represent meaning. So what would it mean for a computer to understand a word? So first of all, let's talk about what it means for you to understand a word. Can you tell me a word that's similar to orange? Tangerine's a good one. Clementine. You guys are really close to the orange space. You're right in orange space. You're all naming citrus fruits. If I got you to go longer, you might say apple. Maybe you'd say banana. So we're like in this realm of things that are sweet and grow on trees, right? citrus fruits. Nobody said car. And nobody said sandwich, even though you eat sandwiches, right? So you have an understanding of what semantics means, what words mean, and I can ask you to sample around a particular point in that space. So you have in your minds a representation of the world, and that's what we're asking you to draw from when we talk about word meaning. So what we need to do is get computers to also build a similar representation. So here is a representation of the world. We have one axis in its sweetness, and we have one axis in its grows on a tree. So all of our fruit is pretty sweet. It all grows on trees, and sandwiches don't grow on trees. Maybe they're slightly sweeter than cars. So they're a little closer to the fruit group than a car is. So this is a very simple vector space model of semantics, a VSM. And this is the computer model we'll be talking about today that represents word meaning. So here, in a vector space model of semantics, every word is a point, and so every word is assigned a list of numbers. So here in the two-dimensional space, the list of numbers will have 2 elements. So here, sandwich is 0 and 0.03 because it's a little bit sweet and doesn't grow on a tree. So every word would get a list of numbers, and that's how we tell which words are similar. They will have lists of numbers that are similar. So you and I know many, many words, and we're able to differentiate between all of them. And that's because we have a very high dimensional space, semantic space. So we're able to tell the difference between many, many thousands of words. And we define the dimensions of language as we learn the language. So my daughter knows what a horse is. If I wanted to tell her what a zebra was, I would just say it's a horse with stripes. And she would understand intuitively that there is a dimension that is stripe, and horses usually don't have stripes, and zebras always have stripes. So we learn these dimensions as we go through life. So we need to get a computer to understand these dimensions in the same sort of way. So we could create a computer model that had the same dimensions as humans, but there's multiple problems with that. First of all, it would be tedious, because how many dimensions do you have to split up all the words in your head? You have maybe even infinite number of dimensions. It's also error prone in that we'd have to get somebody to write down all of the dimensions. And it's subjective, right? If you don't own a dog, you might feel differently about dogs than I do, because I own a dog. Maybe you have a fear of snakes. You feel differently about snakes than other people do. So everybody's own representation of semantics is a little different. So it doesn't really make sense to ask people to write it down. Plus, it would take too long. And I'm a computer scientist, so I have no patience. I want computers to do everything quickly. There's also no ground truth. So like I said, you and I have different experiences of the world, so it wouldn't really make sense for us to try to write down the one true vector space model of semantics for all people. So what we do instead is we get the computer to learn the dimensions automatically, and it assigns each one of the words a point in that space. And so we're going to process a large text corpus. Essentially, we download all of the web pages we can get our hands on. And then we're going to build a model from all those web pages together. So you can sort of think of it as like the average semantic space, because many, many people write those web pages, and we're sort of averaging together their experience. So now, instead of each one of our words having two numbers in the vector, we're going to make these vectors much longer, on the order of hundreds of dimensions. And that allows us to tell the difference between tens of thousands of English words. So in order to do this, to create these vectors for each one of the words, we're going to look through this corpus, and we're going to look for words that are associated with our word of interest. So if our word of interest is banana, we're going to look for all of the times we see banana in the corpus, and we're going to see what words appear nearby. So as you can imagine, banana often appears with the verb eat, probably less with the verb drive. So that would make it similar to the noun apple, but different from the noun car. And you can see how the way that we use words implies something about the meaning. And so that's what we're leveraging here in these computer vector space models of semantics. So this has been going on for a long time. So 1997 was, say, one of the first really popular models of this, latent semantic analysis. And then the one we'll be using today is called skipgram. It was released in 2013, and it's been a pretty effective model. I'll tell you a little bit about it. So skipgram works like this. It is a neural network model, and the task it is trained to do is to predict context words given essential words. So you tell the neural network the essential word is banana, and it needs to predict with high probability the words that will occur nearby. So it's going to predict with high probability 8, maybe high probability yellow. And so its ability to predict those nearby words tells us something about the word meaning. So you can use any large body of text. The one we're using today was trained on Google News, so it's a whole bunch of news stories. And the hidden layer of this neural network, there's just one hidden layer, becomes the word vectors. So sort of the hidden representation that the network learns forms the space in which we place words. So VSMs are kind of remarkable. They can do a lot of different tasks. They can approximate human judgments of word similarity. So if you ask a person to judge, say, midday and noon, how similar are they? They might give it a very high score, 3.94. And the distances between those words in the vector space will correlate with these human judgments of word similarity. They can also answer TOEFL questions about synonyms. So what's a synonym of levied? Imposed is a synonym. And so those two words will be close together in the vector space, whereas the other choices will not be. Can actually perform about as well on these sorts of tasks as students taking the SAT. You might be impressed. Maybe you're not impressed. I don't know. OK, and then also plausibility for role fillers. So like what, given the verb fire and the noun employer, how likely is it the agent? So do employers do the firing? Yes, they typically do. OK, and they can also do something really neat and just track the meaning of words over time. So if we are able to split our corpus up into decades, we can watch how the meaning of a word changes over decades. So for example, the word broadcast used to mean to sow seeds. And now you know, of course, it means something to do with transmission of radio. So vectors are interesting, surprising tool that map human behavior pretty well. There are people who will argue that they're not perfect, and of course they're not, but they're a tool that we have now. So now we're going to talk about how these models that are trained on corpus data relate to what the brain is doing. So what does the brain do when you think of a word? Does your brain representation have anything in common with the vector space representations I just told you about? So here we're going to take our vector space model of semantics, and we're going to try to figure out, does it have anything to do with EEG or MEG collected while a person reads the same word, or fMRI of a person reading the same word? So it's been employed in all three of these modalities, and today we'll just talk about EEG. So in order to do machine learning, we need to take our brain imaging data, turn it into something that a machine learning algorithm will understand. We're going to take it and then try to predict the vector for the word. So in EEG, we do the simplest thing you could possibly do, which is just concatenate all the time series for the time period we're interested in. And that becomes our feature vector. So this is the simplest thing you could do. And it's also, there's lots of room for improvement here. Another thing that we do is we average all the trials for people reading a particular word. So when you read the word banana, we're going to average all of the trials for when you read that word banana, plus we average across all the participants. This is a little different than what people had done previously. In previous work, they would build a model for each subject, and then measure the accuracy for each subject, and then average those accuracies together, and report the average accuracy of a subject-specific model. So here we're averaging across subjects. This might be a little surprising for people who have worked with brain imaging data. Of course, people have different size brains. I think because of the smoothness of EEG, that's why this works. So now we have a brain data average that tells us what the brain usually looks like when you read a word, like banana. We're going to train a regression model for each one of the dimensions of our vector space model. So that's what these betas represent. And we're going to use the brain imaging data multiplied by that beta vector to predict one of the dimensions. So each one of the beta vectors is independent. That means we have an independent model for every dimension of the vector space. Another room for improvement, but another simple assumption we made that actually ends up working really well. Because the brain data is high dimensional, we use a regularizer, L2 ridge regression, which just means that we ask the model to only choose the most important features when it's making its prediction. And so what this model does is it takes as input brain imaging data, and it produces as output a point in their high dimensional space. So it's predicting one of the points in our, if this was sweetness and grows on a tree, it's going to predict a point in that space. And then we can tell what word it is by finding the words that are nearby. So we're going to test our model on held out data. So here in my example, I have 7 words. I'm going to hold out the 2 words mouse and house. And I'm going to try to predict on them what word I think they are. So I'll take my model. I'll give it the EEG data and multiply it by the beta here is a matrix. And so I'll predict a point in space for both this brain image as well as this brain image. So I look at them in space. Here's prediction 1 and here's prediction 2. Now, I'm asking the model to choose between the two held out words. So I'm telling the model, here are two brain images. The words they correspond to are mouse and house. You tell me which is which. So I want to know, is the assignment of prediction 1 to mouse and prediction 2 to house better than the vice versa, prediction 1 to house, prediction 2 to mouse? So here it's really obvious. The green lines are much longer than the red lines. And so we're going to choose the assignment that says prediction 1 is mouse, prediction 2 is house. So this is the 2 versus 2 test. So essentially, we're holding out two brain images, and we're just asking the computer to decide which one is which. So 2 versus 2 accuracy will be the percent of those tests that we run that are correct, and we'll run all possible pairs of words. So in a set of 60, there's about 1,700 word pairs that you could test. And the reason we do this is because you're using 2 predictions to make 1 assignment. So even if one of your predictions is quite bad, the other prediction might be able to compensate for it. So you have better signal to noise. It's easier to tell if your model is better than chance using this 2 versus 2 test. And chance is about 50% because you're choosing from one of 2 choices. So if there was no signal at all, if the brain had nothing to do with word vectors, we would see about 50%. So overall, this is the flow. So we start with a corpus. We run it through this word-to-vec algorithm. We get our vector space model. And then we take that vector space model and the average of all of our EEG data, and we run it through the classification framework. This is our ridge regression to predict points in space. And we run the 2 versus 2 test, and we get our 2 versus 2 accuracy. So what we'll be talking about today is mostly this 2 versus 2 accuracy. It just tells us if there's a relationship between the word vector space and what the brain is doing. So this has been around, I think the first example was 2008 Mitchell paper. So it's been used a lot, and one thing my group has done is actually assembled together a bunch of freely available brain data imaging sets of people reading words and made them available online so that people who build vector space models can test against the brain. So this is BrainBench. We have a bunch of different modalities, fMRI, MEG, and EEG. We also have English and Italian data sets, abstract and concrete nouns, although right now it's only nouns, and growing, so we're always adding data sets when we can. And so here's Dinesh with the same EEG on. So my students are learning to never have a picture taken with this EEG headset on. Here's skipgram. So skipgram performs quite well in this case, about as well as these other 2 models. And because it's quite popular in computational linguistics, that's what we'll use today. So it gets on the order of like 77% 2 versus 2 accuracy. And this is across all of those data sets. Are there questions now? Yeah, good.
I'm sorry, I was going to hold this, but the noun-verb thing got me thinking early, and you said this particular analysis was only nouns. What's your, I started thinking about a verb acting on a noun is different from 2 nouns that are close to each other, and all these things that you probably think about a lot. But what's the, how should we be thinking about that as we're following through this?
So today we're just be talking about single words and they're not in context. There are actually pronouns and verbs and nouns in what we'll talk about today. So we do have multiple parts of speech. And there's some new work coming out of people reading sentences and how that you can use a recurrent neural network, which is a neural network trained to predict the next word in a sequence, how its hidden representations actually relate to the brain. So people are thinking about beyond nouns. But for now, we're just talking about single words. Good. Any other questions?
So maybe I missed this. What was the question for the participants when they are shown this word?
So in BrainBench, there's a bunch of different paradigms. Sometimes they're answering a question like, is it bigger than a microwave oven? Sometimes they're just told to visualize it.
So
There's a bunch of different.
Questions are not related to the dimensions of the semantic vector.
Actually, in one case they are, because the semantic space they used was behavioral. So the semantic space, the vectors were actually made up of the answers to behavioral questions. But often it's just a task to make sure that they are reading and understanding the words. So it can even be like a one-back task. Yeah. Yeah.
So I understand you're saying you use the 2 versus 2 tests to see whether all have 2 images, you have 2 images, can you predict one? Very right. One just has to be better than the other, but if they're both really bad, you still sort of get. They said you got like 77% of that. Do you have an idea for what happens if you give it an image and try to predict it, like see what's the
So the question is kind of, what if you did, instead of the 2 versus 2 test, something more like rank accuracy? So if you had a list of 60 words and you had to choose from the 60, you had to rank them by the distance to the predicted point. It actually performs about on par with the 2 versus 2 test, because you get something, the 2 versus 2 test is essentially rank accuracy with only 2 elements. You can think of it that way. But another interesting thing to do, and you could also have a much bigger set of words.
I might have specifically to the EEG sort of the analysis of that. So filtering, and maybe this is too in the weeds, but I'm just wondering if you pull out like whether what's contributing is oscillatory power voltage, channels.
Yeah, so we'll talk a little bit about the EEG when I get to that part. Oh, we're just about to start. In general, we do the simplest thing. It's like a theme for today. We do the simplest thing you can, which is just take the time series. So we're not doing any Fourier analysis. We do a little bit of ICA to take out artifacts, but it's pretty low key. Okay, so the way that we're going to ask people to learn this new language is using a reinforcement learning paradigm. So we had 24 subjects come into the scanner. They're all fluent in English. They got like a very high score in an English fluency test. And they had to learn this new language while having an EEG cap on. Now at this point I need to give a caveat that this language is actually like an incredibly simple mapping of symbol to word. So it's as if you're learning a new vocabulary. So you're learning which symbols map to words. We're not talking about grammar right now, we're not talking about syntax, none of that. We're just talking about word mappings. Right, and it's by reinforcement learning, which I'll make clear in a second. So we use this ActiChamp. There's 64 sensors, and there's 61 signal sensors. And we collected at 500 hertz downsample to 250. So here's what it looks like in the scanner. So you're going to come in and you're going to see a symbol that looks like this. It's taken from one of 2 Indian languages. And then you're going to be presented with 4 choices. Now, the first time you see these 4 choices, you don't know the answer. You don't know which one of these words the symbol corresponds to, so you choose one, dog. You're probably wrong. 25% of the time you'd be right? And then the next time you see the symbol, maybe you'll choose a different word, maybe choose run, and then you get it right. So it's this process of guessing and getting feedback is how you learn the language in the scanner. So it looks like this. So for 500 milliseconds, you see this funny symbol. And then the choices appear on the screen. And then you have up to 2 seconds to make your choice. Once you make your choice, it turns white for 500 milliseconds. There's some intertrial interval here. And then we give you feedback about whether it was correct or not. And you see the feedback for a second. So we're interested in answering a few questions. The first is there a difference between receiving correct and incorrect feedback? So does your brain respond differently to those 2 feedbacks? And we're also interested in, can we see the semantics of the word you're learning? So if this is you and this is correct, can we see the semantics for the word you at this point in time when you're reading the symbol? So our data set is made of 60 words, and they're randomly assigned to 60 unique symbols. So there's no rhyme or reason for which symbol goes. We didn't choose like a pretty cow-y looking symbol for cow. The 60 words are made of 54 nouns, 3 verbs, 3 pronouns, and they're presented in random order. So that means that every subject sees the words in a different order. And in addition, they're presented a different number of random times for each participant. So some participants see the word cow twice. Some participants will see the word cow 12 times. So we're going to go through a few different results. One of them is sort of one of the more traditional analyses of just an ERP analysis of the signal to see if we can detect reward positivity. So we're interested here in asking, what is the difference between receiving a positive and a negative feedback? So does your brain do something different when you receive positive versus negative feedback? So here is a graph. On the y-axis is the voltage. So this tells us sort of like how much your neurons are firing. And here is the time. And so on this spot here is the onset of the feedback. So this is the point at which they see either a check or an X. And so the lines look like this. If it's correct, you see this more of a deflection, and if it's incorrect, you see this more of a bump here. And if we take the difference of those 2 waves, we see that there's a big difference between correct and incorrect feedback in about 280 milliseconds. So this is typical reward feedback response. And so it's good to see here. So another question we could ask is, as you receive more and more feedback, so you got it right, cow is this symbol, you got it right. The next time you see that symbol and you guess cow, is the response to that different? So you might be expecting the correct feedback, that you will get it correct. So does your brain response look different? And so again, here's the onset of the feedback. And here reward 1 is red, and then sort of mustard, and then green, blue, blue, pink. So you can see that the curve changes as you learn. So this can be interpreted in more than one way. One could be that it's a difference in reward, so it's less rewarding to get it right the second time. Or it could be a difference in learning. You are learning, you've already done a lot of the learning the first time you get it right. So what we can do is average across all 6 of these peaks and then find sort of the grand average peak and ask what the difference is between the conditions for that grand average. So that looks like this. So the very first time you get that correct feedback, you have a large response, and it falls off with a sort of diminishing returns. So as you continue to get the words correct, you are less excited about it. So now we're interested in, we see in the behavioral data that you've learned the language. Our subjects on average get around 83% accuracy, so they've learned the language by the end. Can we tell in your brain that you've actually learned that mapping? Can we see the word the symbol is mapped to using EEG data? So here we're going to take all the words that were presented 6 or more times. This is because we need a good signal of the actual representation for the word. And we're going to average all of the trials beyond the second repetition, so 3, 4, 5, and up as many times as you saw that word. We're going to take the EEG signal from all the sensors. Again, we do nothing special here. We just put them all together. And this is from 0 to 700 milliseconds after the symbol onset. So just like we talked about before, we're taking the brain data, we'll pass it through a model and predict a point in the vector space. And it turns out using this task setup, we get almost 80% accuracy. So we're able to tell what word a person is thinking of when they're doing this symbol learning task. So this was surprising to me and exciting, but there's lots of follow-up questions. So when do you learn the representation? So at what point can we actually detect that you've done this learning? So not on the first trial. Remember, the first trial, you have no idea what that symbol means and you're guessing, right? So maybe by the 3rd trial, or maybe by the 6th trial. So the way we answered this was to average the trials together. So here this includes correct and incorrect trials. So whether or not you got it correct or incorrect, we're going to average those trials together. The red is going to be averaging trials 1, 2, 3, then 2, 3, 4, 4, 5, 6, 3, 4, 5, and 4, 5, 6. And so we're going to see as a function of which trials we average together, whether we can see the word that you should be mapping the symbol to. So the graph looks like this, on Y is 2 versus 2 accuracy. So what we're seeing here is that if we average together the 4th, 5th, and 6th trial, we're able to get almost the same accuracy that we get using all of the data, which means that at this point in time, we can tell that you've learned the mapping. So it's exciting. We're able to see quite early on, trial 4, 5, 6, that you're already learning this mapping. Another question we can ask is, we have the behavioral data, so we know that some of our participants don't learn as quickly as other participants. So some of their accuracy, behavioral accuracy, is just lower. Maybe you're having a bad day, maybe you forgot to have coffee. There's a lot of reasons why this could be. So we want to know, is there a correlation between the 2 versus 2 accuracy that we can get using the EEG data and their behavioral accuracy? So if they are behaviorally worse at this task, are we able to, do they also have worse 2 versus 2 accuracy? And, right. So we had our 24 subjects, and it was pretty clear division of these top and bottom 7 performers, 7 worst and 7 best performers. So we didn't cherry pick this number. So we took all of those with task accuracy below 80%, and they get 2 versus 2 accuracy 59.7, so almost 60%. This would probably not pass a statistical significance test. But if we take those with accuracy above 85%, we get 65%. So there is a correlation between your behavioral accuracy, how well you perform the task, and our ability to tell in your brain whether you're making that mapping. And you might wonder, well, why is the 65 number so much lower than the 79 that you told us earlier? And that's because we're only averaging together 7 subjects here instead of a full 24. So there's a signal to noise problem. But still, we're able to see that those who perform well on this task are actually doing a better job of creating the consistent representation in their minds. And finally, where in the brain is this new language? So again, we have 2 versus 2, where and when. So we have 2 versus 2 accuracy on the y-axis, and on the x-axis is time. So here's the onset of the symbol at 0. So this is the symbol they're learning the mapping for. And at 500 milliseconds is the onset of the choices. And so the graph looks like this. So here we're trying to, with windows of 50 milliseconds, we're trying to predict what word they're thinking of during this part. And here it's still, at this point they're seeing 4 words, but they can see the word that is their preferred choice, if they're doing the task correctly. So we actually get above chance accuracy, so we're able to tell what word the symbol is mapped to very early in time. It starts at about 140 milliseconds, and so it'd be between 140 and 190 milliseconds. And here out much later in time, after they see the onset of the choices, we see another peak. So it's like they have a representation when they see the symbol, and then once they see the word choices, they have another sort of refreshing representation of the same word, once they see that the correct choice is on the screen. So other questions? Mm-hmm.
How different are the representations of each word across individuals? And like,
Oh, across.
Those word mappings among all individuals, how easy would it be to categorize the words in the same mapping? Or is there some sort of bleed over in terms of the representation of the word that you get from one individual and representation of a different word that you get for a different individual?
So people are remarkably similar in their understanding of words, even if they have different opinions about them. So I don't know if you could do it with EEG data, but they've done it with fMRI, training on one person and testing on another. And it works for some people, not all people. Because we do agree about a lot of the things in the world, especially nouns. The kind of nouns we're talking about. So you understand what a chair is. There's not much disagreement. Yeah. And do you have a question?
Yeah. So are these trials only ones where they've gotten the correct answer? Do you see the kind of rebound accuracy when they get the trial wrong?
So this is so this is everything. So this would be trial 3 and on, and we didn't actually select for correct trials, but it mostly contains correct trials at that point. Yeah. Mm-hmm.
Are you interested at all in reducing the number of channels to see like how accuracy?
Yeah, so we'll get to that in a second. So one of the questions we are also interested in asking is where in the brain is this representation showing up? So, I mean, these are caveats, of course, because we're using EEG. So that's a very smooth representation, but that's one of the things we'll talk about. Maybe just one more question? Yeah.
Just one clarification. Are you relearning the betas or using the ones that you learned in the just English language?
So here, every point in this graph represents a new set of betas. But one good question would be, what if you took the betas you learned during that early peak and applied them everywhere else? What would that look like? So that would tell us, that would answer for us the question, is the representation of the word when you're reading the symbol the same as the representation of the word once you see that word on the screen?
I was also interested in like when you're learning the word in English, for example, versus when you're just learning the symbol, if those weights also are similar, right?
Learning the word in English?
So there's some betas that you learn like in your previous examples, just when you're talking about English language itself, right?
Oh,
The mouse example.
Yeah, so none of that was in EEG. And I guess it kind of gets to the intersubject question that, like, could we use this across subjects? And sometimes yes. Okay. So we're also interested in where in the brain this signal is showing up. So at what EEG sensors do we see this representation? So here, each one of these points represents an EEG sensor, and we're using not just that point, not just that sensor, but all of the sensors in its immediate neighborhood in order to train the model. So this is from 0 to 400 milliseconds. So this is the time they're viewing the symbol. This is mostly the time they're viewing the choices, and here's an average over the full 1 second. Excuse me. So here, there's a few, I don't know if you can see, but a few of the points are white. White points are significantly above chance. So actually, during the time that they're reading the symbol, none of the sensors by themselves can actually predict what word they're reading, the word mapping to the symbol. So that means that this representation in this early point is pretty weak. It's not as strong as we see later. So here, during the time they're reading the choices, including the word they know is the correct word, we see a much more robust, strong representation. And so individual sensors in left temporal can, by themselves, tell us what word they're reading. And if we take the full average, you see an increase in the number of statistically significant points, meaning that there's some complementary signal across the two time periods. So when we put them together, we get a better model. So it's not like everything before 400 milliseconds is noise. There's some additional benefit for including that in the model. So now I'm going to do a little bit of wrap up and talk about what we talked about today and why it's interesting. So we went through a lot of results and sort of like, why should you care? So we can detect the reward positivity as people learn this new vocabulary. That is that we can tell that they have a different brain response for when they get a word right and when they get a word wrong. And we can also see that the reward reaction diminishes over correct trials. So as you learn the paradigm, as you learn going through the paradigm, your brain response to the correct trials diminishes. And so this could be either because there's less learning on these subsequent trials or because the reward is less great, because you knew it was coming. It's an anticipated reward. So we can also now, we can detect the semantics of the word during this learning trial. Now this is important because some of the past work doing this word vector analysis has had some criticisms. Some of those criticisms are, do you know these vectors actually have anything to do with semantics? Right. They could be just the visual features. And actually there's a correlation between word frequency and word length. So words that are frequent are shorter. That's just a function of language. It's not something we can get around. And so something that's a little semantic, something like word frequency, has an effect on the word form. And that means that there will be fewer white pixels on the screen when you're reading words that are more frequent. So how can we tell that what we're doing is actually decoding a semantic signal? And so the work that I talked about today, because we're not showing the word, we're showing arbitrary symbols, is a good piece of evidence that what we're actually decoding is semantics, because these symbols are arbitrarily chosen. The mapping doesn't have anything to do with the word. And we're also not coaching them to visualize the word. So a lot of previous work had asked them to just, beforehand they asked them to imagine all the words, and then in the scanner they were supposed to imagine the word for 3 seconds, and that's not very natural. It's not what people do when they read. And so here this is a very engaging paradigm because you're doing this learning task. And it's enough to engage people to create those semantic representations that we can still pull them out with this technique. So we can also detect this learned representation as early as trials 4, 5, 6. So even though we're including correct and incorrect trials, trials 4, 5, 6 are enough to tell us what the word is that you are mapping to that symbol. And we found also that behavioral accuracy correlates with the 2 versus 2 accuracy. So even though, so we can tell how well you are performing on that task just looking at your 2 versus 2 accuracy. So this could be useful for things like determining the difference between a correct guess and somebody who's actually learning. Now we also see 2 peaks in this 2 versus 2 accuracy, which I think is maybe one of the more interesting results here. So we're at the very beginning when they're reading the symbol, we see this short peak. And then we see, once they see that the correct word is on the screen, we see this much more robust representation of the word. So the question is there a mapping between these two states? Is there a similarity between the time they're reading this symbol and the representation they pull up when they read the actual word? And so one of the ways we could test that, and we're working on right now, is if we trained a model just on that early point, that high peak during the symbol reading part, can we test it later in time during the time they're reading the actual word, and can we still predict with 2 versus 2 accuracy? So this is if you may have heard of it, a time generalization method technique where we're training and testing across different time windows to see how the representation changes over time. So we see even with this though, we can tell that there's a difference between the semantic representation for the symbol and the one they pull up when they're reading the choices. So the first thing is the symbol representation appears later. It's about 40 milliseconds later, and it's much less, it's sustained for much less time. So it's just a little peak and then it's gone. Whereas the time when they're reading the choices, it's a much longer peak, although it's a similar accuracy, which was surprising to me. And the peak that happens after you're reading the choices is earlier. We also saw that the distribution, the sensor space told us that the representation during the time you're reading the symbol is much more distributed. It's weaker, and none of the sensors by themselves could tell us what the word is. We needed all of them together. And so this is different than when you're reading the choices, when individual sensors were enough. So this tells us that the representation during symbol reading is not as robust. It's a weaker signal. So in the future, there's a few ways we could go with this. One of them is I've already talked about, which is if we trained a classifier during the time you're reading the symbol, does it perform well if we test it during the time you're reading the actual choices? So is there a similarity between those two representations? And we can also extend it to other learning scenarios. So I think it would be interesting to test what representations look like when people are learning to generalize to new stimuli. So if I told you, if you'd never heard of a zebra, and I told you that a zebra is a horse with stripes, what does your learned representation for a zebra look like? And we can also talk about different ways to do curriculum presentations. So is there a way to present trials in a particular order so that it helps people learn? And with that, I'll actually ask for questions and email me if you have any other questions. And you'll never pronounce my name wrong ever again. Right? Uh-huh.
So I'm thinking about comments people make about different kinds of learning. So some people say they're visual learners or auditory learners. So the issue is, I mean, I'm sure you got lots to do. It looks like you focused on vision. But what about even braille or touch or sound? So do you have any predictions?
That would be interesting. So we would play them a word, and then we'd either play them the English word or we'd show them the English word. That would be interesting. I have thought about how that would work. It's an interesting idea, though. Yeah. Sure.
So I was looking at your model, and basically the way you're doing is you are showing them a new symbol and then associating that with a word, right?
Mm-hmm.
And then there is an actual representation of the object that is associated with that word. So when I was thinking about this, I was thinking of there are two ways of learning a new language. The way in which you start translating to your native language, and then a way that sometimes they say it's a more robust way of learning, which is basically just associating the new word to the actual object.
Mm-hmm.
So I wonder, how is that?
That's sort of interesting. I guess his question, the question is sort of like if we encourage people to not translate, because what we're doing is we're actually getting them to translate. We're showing them the word, and so we're encouraging them to do this mapping to words. But we could instead show them, it doesn't work for all of the words, but we could instead show them pictures. Like we could show them a picture of a cow. So this symbol for cow and then a picture for cow. And maybe that would be a different, show a different kind of response. That would be interesting, yeah.
So I was wondering if probably the response that you get after they see the actual word may be due to the second association to the actual object.
Yeah. So I think, so there's a whole bunch of work that shows that reading is very automatic, and sort of like the representation that you pulled up when you read a word is quick and not something you have a lot of conscious control over. So I think that's what's happening is they're reading once they see that correct word, it's like their brain just does, because they're also seeing 3 other words, right? But they're able to focus on the word that they know is correct. Yeah. Mm-hmm.
It occurs to me that when you do a task like this, that there's kind of 2 kinds of representations I'm forming. And you talked a little bit about this. I'm making a visual representation of like what the symbol looks like, and then I have a conceptual representation of what it actually means. And I'm wondering if you could speak to what evidence you have that the model is not relying on visual representation.
So this is a great question. Yeah, right. Yeah. So the way that we test statistical significance for these models is called a permutation test. So we take all of the sort of assignments of which brain image have corresponded to which word, and we shuffle them. So if we were just learning some correlate of vision, if the word vector had really nothing to do with it, and we could sort of like hijack it and predict something that had to do with vision, then when we shuffle it, we could still do it, right? And so we can't. Or at least that's what we're testing against. When we say it's better than chance, we're testing it against a model that had that situation, where the words were shuffled. The semantics no longer lined up with the actual brain image. And so if you're interested, that gives about 50.01% accuracy, so very, very close to 50%.
What would happen if you were to do this experiment, but the second, like the conceptual thing was actually just another arbitrary symbol? So you're just doing arbitrary symbols.
Oh, arbitraries.
That's like learning, but it's not the semantic learning because there's no semantic learning at all.
That's interesting. So if we, instead of showing the words, the next screen that came up would be, say, a set of 4 symbols, and you had to choose which one was right. So you would be learning association from symbol to symbol. And then I think the science question would be, can you see some of the visual features for the second symbol during the time you're reading the first symbol? That would be interesting. I'm not sure. I would think maybe you might be able to do that in a different modality, but EEG is very smooth. Yep.
On my mind, I wanted to ask what you would expect if you only recruited participants who recognize the symbols as letters.
Oh, so because you're an Indian speaker, you know these letters. So if we only took people who speak an Indian language, I forget the 2 that we chose, Tamil and
One of them was
Hindi.
Tamil, I'm not
Yeah.
sure.
So we both know one of them. That's good. So that's interesting. So if the response would be different if this was your native language, that's interesting because you could build sort of like memory devices in. The thing that I always find hard about this task is you're seeing these symbols and you're like, I don't know, curvy thing with the stick on top, and then that's you, I guess. And you're trying to build these associations, but if you actually knew what that actually meant in the language, then you could actually build a better representation. That would be interesting. Yeah. Yeah.
I'm curious about the time course of the prediction from neural data to image or to meaning of the word versus the person's accuracy. And so would there, I guess I'm thinking about like if I'm learning, sometimes I don't think I know it and then
Yeah.
find out the answer I remember.
Yeah.
So would there ever be a situation where the neural data is better at predicting the outcome than the person?
Oh, so it's interesting. So I think the question is something like, if you ask people, so they see the symbol and then you ask them before you show them the choices, their confidence, and do they think they're going to get it right? Would that correlate with the sort of strength of their neural representation when they read the symbol? I think that's a really interesting question. So whether this like sort of introspection correlates to if you can tell how strong your semantic representation is. I think there's a bit of personality in there too, right? Because you're it depends on what your kind of person you are. I mean, some people just aren't as sure about their answers.
I just had a question about the time course. I was wondering why you think that the neural representation doesn't persist until the onset.
Yeah.
Because then there has to be some way to remember
Yeah.
what you saw or something. So there's the neural representation.
Yeah.
Yeah.
It's a good question. So the question is, so why do you see that one little peak and that goes away? You have to remember the word, right? It's a good question. I don't have a good answer for it.
Could just be maybe the limitation of EEG or.
But you think if we could detect it at one point, if it was still there, we could still detect it. Maybe it's not as strong. That might be true. I'm a bit of a cautious person, so I would imagine I would do not very well on this task. And I could imagine when I think about what I would be like if I was doing this task is like, cow. Oh, is it cow? Maybe it's horse. And so that's what you're saying. You see like cow, and then like the person is like deliberating internally, and then they see the choices, and cow. But
I can follow up on that. Are you using the same regression coefficients both early and late, or do you
So we train them.
separately?
We train them separately. I do have some really preliminary results of training during that very first time and testing later, and it actually doesn't look like there's a very good match. But we haven't had a chance to really like dig into that deeper yet.
For the individual neural signals that were predictive of what word they saw, did you look to see if they're like functionally connected? Or there was, like,
Right. So our model is, as I said, the simplest model you could possibly train. So it doesn't know anything about which centers are close to each other, and it doesn't do any sort of correlation analysis or try to project it into a lower dimensional space. There's nothing on top of it, but of course all of that could help here. L2 regression does have the property that if there are a set of correlated variables, it will sort of spread the weight across that group, but nothing beyond that. Yeah.
I have a question, like, the two figures, one where you show the early peak, that we were talking about, and then the one where I was looking for that spatially, and there was something reliable, right?
Yeah.
So I was thinking that early effect might be something like perceptual priming, and then what happens later is more like semantic elaboration, contributing to your classifier performance.
So what would perceptual priming be in this case?
So recognizing the simple at an implicit level. The earliness of it made me think that it was not explicit awareness, but perceptual,
right.
implicit memory.
I see.
If that were the case, then maybe you could analyze the EEG data and have get features that would give you better classifier performance in that early window.
And like what kind of, I'm interested what kind of features.
Yeah, so I mean, you iterate over electrodes, right?
Mm-hmm.
So maybe like gamma would be.
Yeah, so like a frequency analysis. Yeah, that would be interesting. Yeah, there's lots to do here.
Let's take one more.
Okay.
before break.
How do you think the results would differ if they had extensive exposure to these symbols, right? Because all of the words that are corresponding to the new symbols are super familiar words, and they're nouns, they're things that we've all physically interacted with. But the symbols are quite new.
Yeah.
Only visual. So do you think that you would maybe see a change in what you call the robustness of the neural representation, or how do you think the results might change if you have really extensive training?
So do you mean sort of if we ran the reinforcement learning paradigm for longer and we use the data from later?
Yeah, and maybe different types of training and things that maybe forcing them to use these words more naturally. Just giving them more experience
Yeah.
with the actual symbols.
I think you're right that
might affect your results and maybe allow some of that might maybe cause some of the signals in the earliest time point, the 0 to 100 milliseconds. You might then be able to use that EEG data to actually predict
Yeah.
use that as a predictor for your vector-based model.
Yeah, I think you're right that if we went for longer and maybe used an additional task in addition, I bet it would become more robust. And that would be good because then maybe we could train at that time and test everywhere else and it would work. Good.
Thank you all for coming. Please enjoy the reception outside. Thank you again.
Thanks. Great question.